Hello everyone, my name is Samir Surya and I'm a project manager at CONVERGE Science. I'm part of the support and applications team. Today we are going to look at how to set up a hydrogen engine case. This is part of our example cases. If you go if you see my screen, now if you go to File, Load Example Case, IC Engines, and then navigate to hydrogen spark ignition, and you can see this engine Sandia hydrogen DI engine Sage transient runs. If you click that, this case comes up, but we are not going to talk through this process today. What we are going to do is we are actually going to set this case up from scratch. So we are going to set this case up from scratch. Now, one of the first things you should do is to have this CAD model from your CAD software. I would highly recommend you flag the boundaries. Flagging means you have the head separately, the intake port, the exhaust port, all grouped separately, and bring those into Studio. So you could actually go to File, Import. If it is a CAD file, you can import a CAD file. If it's in STL, you can import an STL. And once you bring it, all the flagging that you have actually done for these different boundaries will come into CONVERGE. Now, I took the geometry in such a way that the boundary names are not preserved, so I could actually talk through that. So one of the first things that we are going to do is to identify what those boundaries are, and I'm going to show you how to do that. So boundary 1, I know this because this is one of our engine cases. So what we are going to do is fill up these names and then proceed from there onwards. So my boundary 1 is cylinder head. So if you right click on this, it will allow you to change that. So you could actually type head. Boundary ID 2 is your liner, and then boundary ID 3 is your piston. So it's simply identifying these different parts of the geometry, so you can use them later on. Boundary ID 4 is actually intake port. So I'm just going to call it intake port, IP. Boundary ID 5 is your exhaust port. Boundary ID 6 is your exhaust valve top. Now we'll talk about in a little bit as to why I'm breaking the exhaust valve into 3 different parts. Then boundary ID 7 is my exhaust valve angle. And then boundary ID 8 is exhaust valve bottom. Going into the intake valve, boundary ID 9 is my intake valve top. Then intake valve angle. And then intake valve bottom. Boundary ID 12 is my intake boundary. So if I show you that, you go into view options, you can see the intake comes up. So right here, these are inlet boundary. So that's my intake. I'm going to call it intake. Boundary ID 13 is your exit boundary or exhaust. And if I show that to you right here, so you can see right over here, that's your exhaust boundary. Boundary ID 14 is your hydrogen inlet for the injector. So it's a gaseous hydrogen injection, and that would be right there. So if you follow my right here, that's your hydrogen inlet. boundary ID 15 is the piston skirt. So the piston is divided into two parts here too. That's a preference and like what you want to do with your simulation. So you don't have to like do this exactly the same, but I'm just showing you how different boundaries can be flagged. Boundary ID 16 is going to be the, if I do it right here, so that's the injector sac where the injector sac joins the head. So let's call this the injector sac. The names doesn't matter. You can give whatever the descriptive name that you want. And boundary ID 17 is a tumble fixture. So here, right here, in the intake port, if I remove the intake port right here, you can see this tumble fixture. So that's your boundary ID 17 right here. And let's call this the tumble fixture. And boundary 18 is the injector wall right here. So let's call this the injector wall. And then boundary ID 20 is your spark plug, which is right about here. Let me remove the head boundary so you can clearly see it. Remove, so boundary ID 20 is that right there. So let me call this the spark plug. Okay. Now you are done naming the boundary. So you can see the intake valve has been divided into three different parts: the intake valve top, the angle, and the bottom. Why we do this is actually in IC engine lecture slides. So I invite you to go through those and learn that process as well. Now we are not, this geometry is like clean. We are not going to talk about surface cleanup today. There will be a different lecture to talk about surface cleanup. So now that you are done flagging your boundaries, everything looks good, there are no surface errors, we are ready to do surface case setup. Now you go into your case setup doc. If it is not already there, you could actually go to view and then turn on from here. You would click on begin case setup, and the first question we ask is it going to be time based, meaning is the time calculated in terms of seconds. If it is engines, we calculate, it is time based, but we calculate time in terms of crank angles. So I would click on crank angle based IC engines. You hit apply and done. CONVERGE figures out certain bare necessary inputs that you want for an IC engine case, and then it populates. We would need more. For example, like there's no combustion panel here. We would have to like go and turn that on later on. So let's actually go in order and try to set up this case. The first thing is the you click on the crank angle based IC engine. This is where you give the cylinder bore stroke information. For this engine case, I know the cylinder bore is 0.092 meters or 92 millimeters. The stroke is 85 millimeters. Remember, like the inputs, CONVERGE takes it as in meters. So it's very important that you include the numbers in meters. So the connecting rod length for this case is 667. There is a crank offset for this engine. So that's 3.7 millimeters. We don't have to like give any swirl ratio here because we are going to do the intake process, and CONVERGE will calculate the swirl and tumble automatically. The head position is 0. This is for velocity initialization. And then the crank speed or the engine RPM on this is like 1500. We are not going to like use Crevice model for this one. Now we need to give tell Converge what is the piston ID, line ID, and head ID. This is again for velocity initialization. So piston, I would give piston, liner, and the head. Again, this classification is for velocity initialization. I would hit validate and OK. You can see the green check mark came in, and that means Converge says you have entered all inputs and the input seems correct. Now, it doesn't know, it is not smart enough to figure out if you give your cylinder bow wrong. If, for example, if the actual diameter of this like liner is, let's say, 100 millimeters, and you gave 92 millimeters. Converge is going to use 92 millimeters when it is going to calculate things like, you know, piston speed and stuff. So it is up to you. Converge is not going to verify, okay, in your geometry it's 100 millimeters, but you have entered 92 millimeters. It is up to you to correctly measure this geometry and then give the correct value over here. Now, under materials, since I'm going to do a combustion simulation and it's going to be detailed chemistry, I want a reaction mechanism. So I'm going to like, you know, hit apply, and then you can see the reaction mechanism part came in. Now let's move on to gas simulation. We are going to use an equation, a Redlich-Kwong equation of state. We have access to like, you know, several real gas equation of states and ideal gas, and we are going to use an real gas equation of state, in this case Redlich-Kwong. Because it's hydrogen, we are not going to use single species diffusivity. We are going to use mixture average diffusivity and mixture average viscosity and mixture average conductivity. Now, when you select this, Converge would require a data file called transport.dat. You click on that, it says yes, you have to import a transport.dat, and then you click on this button right here to import a file. So you would go and you need to have this file. So you are not going to make this file in Converge Studio. This file comes with your chemical mechanism. If you don't have access to this, contact support and we should be able to help you with it. And you import that and you hit OK. Now, so that's like for transport data, and then for thermodynamic data, again you have to import a file called therm.dat, and here you click on this button to import therm.dat. Converge automatically populates a default therm.dat, but if you are using a particular mechanism, I would highly recommend that you use the therm.dat file that came with that mechanism, and that's what we are going to use today, therm.dat right here. And then hit validate, OK, and I validate it here. There is a, so Converge said I found an issue. So let's actually go and look at case setup issues, and it says, yeah, transport that file. We have already given that. So I think, let me import it. Maybe it didn't get imported again. Import that, OK, validate, yeah, it goes away. So again, Converge Studio provides you with error checks. But it doesn't like, it can't check for a particular input error if it is not trivial. For example, whether the bow size is like 100 millimeters to 92 millimeters. But if you have not input a therm.dat or transport.dat, just like what we just saw, Converge is going to say, hey, I think you need a transport.dat, but you haven't included that. Please import that. Let's import our reaction mechanism. Again, I would go and import. This is not something that you would make. I would import that, and there is this button called check properties. What it does is for all of the 12 species, so let me actually show you that. So this is our mechanism that we are going to use, and that's actually from our C3 mechanism. So this is extracted chemistry from C3. It has 12 gas phase species right here. And for all of these 12 gas phase species, you need to have thermodynamic data, and when you check this check property button, it double checks with the term.dat we just imported. So validate, OK. So now that's done. Now we are going to move on to setting up the simulation time parameters. So if we move on to run parameters right here, so it's going to be a new run, and you can actually rename the file. For example, the surface file name, I'm going to call this the Sandia hydrogen engine.dat. I like to rename it to like meaningful surface file names so that you could keep different surfaces differently. I know, like, from case A comes surface file A, case B comes surface file B. It's a preference. CONVERGE really doesn't care as long as you have this name the same in your surface file name. It's going to be a transient simulation, and it's going to be crank angle. We see all of these inputs CONVERGE automatically populated as soon as you said this is going to be a IC engine simulation. Now go to miscellaneous, screen print level, we can keep it verbose. We are going to like solve internal energy, we are going to solve species because there's going to be 12 species that we are going to transport. All of this is good to start with. File names, the mechanism file name is mech.dat. So I think, like, we are good on this. So now actually let's go on to simulation time parameters. This is where we say from which time we start and from which time we would go until. Now I want to set it up like, so that we can run from IVO to EVO, but I want to run 2 cycles. So I know my IVO is at 374. I'll actually verify this with you later on when we import our valve lift profiles. You will see that IVO is at like 374, and my EVO of the second cycle. So EVO is at like 120, but like I want to run 2 cycles, so my EVO of the second cycle is going to be 840. I'm going to use a variable time stepping algorithm, which is recommended for engines, and with this you need to specify some time steps. Initial time step, I would start at 1e minus 7. So let me that 1e minus 7. The minimum time step I would want 1e minus 8. The maximum I would want it 1e minus 4. Now the convection CFL number, and there are some other time stepping limiters that we use to figure out this variable time step. For example, convection CFL determines what's your velocity, fluid velocity is, and tries to limit your time step. The Mach CFL looks at like what the speed of sound based on temperature and limit the time step. If you have liquid spray, which we don't have in this case, it will look at how much time in one time step, how long or how far a particular parcel would actually propagate, and try to limit your time step. What we would use in this case is the chemical time stepping control. The value of 0.5 says in a particular time step, if the temperature of a particular cell goes above 50% of its current temperature due to combustion, that time step is too large. We would move back, cut down this time step, and move ahead with a smaller time step. So for now, let's actually have keep the CFL number as 1, but I want to like show you how to use this file option later on once I set up all the boundaries and events as well. So for miscellaneous, we could actually use the default parameters. Now let's move on to solver parameters. Solver parameters gives you all of the Navier-Stokes solver type that we are using. Are we going to use a density based or pressure based, and the convective flux schemes. For this case, like you use the set recommended settings for a transient gas compressible case, and that's all we need. So, but this is where like you would have all for pressure, momentum, what is the solver type you are using, how many iterations you are using. You have all the control for that. Unless like you have worked with these a lot and have changed it, I would recommend you using the recommended setup as a starting point, and then change them accordingly based on what you want. Okay, now let's move on to setting up boundary conditions. So you click on this, and then your boundary condition menu comes up. Now you can see here you need to specify two different things. Like here you have to specify the boundary conditions, and you have to specify the region this boundary belongs to as well. We haven't specified the regions yet, so we would actually come back to it later. But let's actually start like filling out this. So the cylinder head boundary is a wall boundary. So you select from here, it's a wall boundary. And then it's a stationary because the head is not moving. And the temperature I want for this is 353.15. You can, this actually has to come from your engine data or like, from other measurements, but this is important information to get it right. I am going to use so there's no surface roughness. I'm not going to apply surface roughness. Heat model, you can apply it as global. I'll talk about it when I'm in the turbulence modeling section, and everything else looks good for this. Now let's move on to liner. Again, a wall boundary. It's a stationary fixed, meaning it's not moving. The liner temperature is again 353.15. And everything else looks good on this one too. So you can see when I hit validate, it went through everything and it says, wait a minute, there's no inputs. There's a lot of like, missing pieces. We know that. So it'll disappear as we keep on doing this. So now let's come and set up for piston. Piston is actually moving. So we need to set this up. It is not going to be stationary. It's going to be a translating moving boundary. So wall motion type translating tells that it's actually the boundary condition applied to it is actually a translating boundary condition. Surface movement is actually the physical movement of the triangles, and in this case it's physically moving. We are in CONVERGE because we do like a lot of IC engine simulation. We kind of like have a shortcut to specify the piston motion. You don't have to specify a location file or like velocity of the piston. We can calculate all of that using the information that you give here as per the crank slider mechanism. So, and that's what we are doing. You just click on the piston motion and CONVERGE knows, okay, this is a piston. I need to go to crank slider mechanism, calculate all of that and apply that. If you want to look at what that piston profile looks like, you can select it over here. Now, the temperature of the piston we want for this particular case is again 353.15. Everything else looks good on my data sheet. Now I am going to go into intake port. Intake port is a wall boundary. It is not moving. Intake port, I'm checking my data sheet. It's actually at a lower temperature. On this case, I want 10.15, and then everything else looks okay. Exhaust port, again a stationary wall boundary condition, and then that is at a higher temperature compared to the intake port, so I'll put 353.15. Again, these values you need to get it from either measurements or some experience that you have with your engine. Intake valve top. Okay, so now we get into valves. Now, valve boundaries, these are again walls, but they are not stationary. They are moving. So it is translating, moving. Now, we don't have a shortcut for this. It has to be user specified. That means you as a user needs to specify what these values are. So here it's going to be a profile, so I'm going to use profile, and it brings you to this menu where you could actually specify your valve lift profile. You can type it, but that's kind of like not common. Essentially what we do is we bring in the valve lift profile from your engine testing. So you actually click on the import button. I have the exhaust lift file. It essentially says what's the direction of the valve moving, and minimum lift. If you are not familiar with this concept of minimum lift, like, I would highly recommend you go to our IC engine training slides and review that. So essentially in CONVERGE, the valve doesn't close all the way. It actually has a minimum lift that it maintains, and there's not going to be any leakage. We discuss all of that in our training slides, but that's this minimum lift, 0.2 millimeters. And you can actually plot this and see if everything looks fine. So it's an exhaust, so firing TDC is 0, so it actually opens around like somewhere after 100 and then closes somewhere after about like 350 or so. Everything's good. And the name is exhaust lift.in. I would say accept. And then that's good. And exhaust valve angle, even though we break the valve into 3 parts, everything should be moving as one piece. So it's again a wall bound, hold on, it's a wall boundary, it's a translating moving, and for velocity I am going to use the same file, exhaust lift.in file. I accept this, say yes, and I validate, and everything looks good. I think I forgot to change the temperature here, so it's an exhaust valve. It should be at high temperature, and then EV angle, so the exhaust valve angle also I'm going to give the same temperature. Exhaust valve bottom, let me check my data sheet again. Exhaust valve bottom, similar concept here. Wall, it's a moving wall. So I'm going to use the same exhaust lift file from my engine data. Accept, yes. 353.15. So exhaust valves are done. Now going to intake valve, similar concept, but we can't use the same profile. We need to get the intake valve profile. Again, you need to have that from your engine testing. It's translating, moving, and then we use a file. This time it's the intake lift.in file. The temperature is relatively colder. I'm going to 9, and then the intake valve angle, I do the same thing. Sorry, yeah, that's right. It's a translating, moving. For velocity, I bring in the profile. Intake valve bottom, it's a wall boundary, again translating, moving, bring in the intake valve profile. You can see that starts somewhere around 350 or so, goes till about 590 or so. This is good. Now intake valve bottom is open to the combustion chamber, so theoretically it should have a higher temperature. So I'm going to use the exhaust valve temperatures at the bottom of the intake valve, and I validate that. Okay, so the next boundary that we need to set boundary conditions of is like the intake. So this is the air intake. So I click here. Now you can see it's no definition. I get it. This is an inflow boundary. So it's going to be an inflow. Now, because this is a subsonic inflow, AI inflow, I want to set up like the total pressure. In CONVERGE, you can set this up in two ways. You can give a constant value if that's what you know, or you could give a file. And in this example, I'm actually going to use a file. You click on that button, and then here you can include the crank angle and the pressure values for your total pressure, or if you already have it in a file, you can import that. So I already have that file, so it's called intake pressure.in file. I import that. The name appears here too. It's a cyclic 720 period, and I hit accept, and then it gets accepted. Now for the temperature, so let's look at my data sheet. The temperature should be 309.15. Again, like you have to look at your boundary condition values from your engine testing to get the intake air temperature. Because this is just air, and I can click on this button right here and get the species mass fractions. No passives are defined from this intake. The turbulence values of 2% intensity and 3 millimeter length scale for epsilon boundary condition is good. So you can hit validate on that. So the air intake is done. So the next one is the exhaust boundary condition. This is the outflow. So it's an outflow. I select the outflow. Now outflow boundary condition looks a little different. This is a subsonic outflow. I'm going to specify pressure and temperature. So the velocity is going to be Neumann. Again, just like intake, you can specify a single value, or if you have access to crank angle resolved pressure values, which is more accurate, you can give that. So I'm going to click on that. Similar concept here, you can import if you have that pressure, exhaust pressure.in file. I import that and I hit accept. Now, temperature condition is a little different than the intake. We want to specify something called a backflow in the outflow conditions. Now, just because you specify a backflow condition doesn't mean there's flow going to come into the domain through the outflow. What it means is if the pressure conditions are right, and if some mass was going to come in, you are specifying what's the conditions of which what's coming in. So whatever's coming in from the outflow domain, it's going to be hot exhaust gas. So let's look at my data sheets. It's 800 Kelvin. Now species, if you think about it, this is the exhaust port. If whatever's going to come into the domain, into the exhaust port, it has to be exhaust products. So we need to specify those species. You can click on this button to add a species, and my exhaust products for hydrogen combustion, it's like H2O. I know this from my data sheet. So you would actually know it 0.12. So based on your equivalence ratio, you can calculate what the exhaust products are going to be. I add nitrogen. My data sheet says it's 0.759002. You don't have to be this accurate into decimal places. CONVERGE really doesn't care as long as you decide the composition is accurate. That's all we need. Just because I have access to that, I'm just going to type this out. 3357. Okay. You're going to make sure that mass fraction adds up to 1. Again, no passives. Intensity and epsilon is the length scale is good enough. So if you hit validate. The next boundary condition is the hydrogen intake. So you click on that. It's again an inflow boundary. And now this is going to be you can actually give a pressure, total pressure case, just like we did it for intake, or if you have access to mass flow rate, you can give that too. So I'm going to demonstrate that. So now we are not going to specify pressure Dirichlet, it's in fact going to be pressure Neumann, but for velocity boundary condition, it's going to be a mass flow rate boundary. And here I'm not going to specify one single value, which you can if that's what you have. I have a data file again for this one here, and hydrogen mass flow rate. And I specify that if you can actually look at this as well. So this is how the profile looks like. At a particular crank angle, you have the hydrogen coming in, and then it stops injecting. So you can accept that. Now, this is a hydrogen inflow, so everything that comes in, all the mass should be hydrogen. So the species is 1. No passives. TKE is still 2% intensity is okay, but because this is coming from a smaller like tube, 3 millimeters might be too big. So we would put a value like 4. So typically like about 10% of your intake diameter. And this is good too. Now, before I move on to the next, setting up the next few boundaries, let's actually go and show you these boundaries that I set it up. So you can go into view options. You can see the intake boundaries number 12. So that's your intake boundary. So you can clearly see the intake boundary. That's the boundary condition that we just specified. And then on the other side, you have the exhaust boundary right here. And your fuel intake or the hydrogen intake that we specified is right here. Okay, now let's move on to setting up the piston skirt. Now, piston skirt boundary is part of the piston. Let me actually show you that the way we have done it. So you can see the piston crown. We have set it as piston, but the crevice of the piston up until the first oil ring, it is being set up as a different boundary. Now there can be like several reasons why you want to do it. You can do this like to give a different temperature, or give it as a different, specify it as a different region, but we want to like show you that this can be done. So we go to piston skirt. This piston skirt is part of the piston, so it has to move with the piston. So it's actually a translating moving boundary. It's a piston motion. It should have the same piston wall temperature if you want to, or if you think it's like at a different temperature, you can give it as well. And then the injector sac, it's a part of the head boundary, so it's a non-moving wall, and I would give the same temperature as the head. And then the tumble fixture, it's in the intake port. It's again a wall. It is not moving. And I would give this as the same temperature as the intake port, which is the 309.15. The injector wall boundary, this is the tube of the injector. It is not an inflow, it is actually a wall. It's a stationary wall. The temperature is again, you can actually include the temperature. Again, it has to come from data. So I'm going to call this 309.15. If you want it like higher, you can like do that higher as well. Spark plug, non-moving wall, but spark plug should have a higher temperature because it gets pretty hot during combustion. I would put something like 550 in here. So that actually concludes the boundary condition, but remember, like, you need to specify the region definitions. So now I think we need to specify the region definitions, because without region definitions being set up, we can't go back and correct the boundary menu. So in this case, I want actually 4 regions, one for intake, one for cylinder, one for exhaust, and one for the injector, because I want to cut off the injector flow rate when the flow rate when it is stopped injecting. And because it's a gas injector, it's if I show you one more thing real quick, if I remove the liner and like look from here, there is no physical partition here, and in the code we need to like tell CONVERGE, you need to put a physical partition here. This is called the disconnect triangles if you have taken an engine class. And then in order to do that, the cylinder region and the injector region needs to be in 2 different regions. Okay, so let's actually go and set that up. So go back to case setup, regions and initialization. Now you are going to add, so let's go ahead and add 4 different regions. So my region 0, I'd like to call this the cylinder region. Again, double click on this, you would get to change the name. I'll call this a cylinder. My region 1, I'd like to call it the intake. Region 2, okay, so now you can see that it put a @ sign. This is because I've already used the word intake as a boundary condition name. So what I'm going to do is intake space, I give a little space, or like you can call it intake region, a unique name. Exhaust region, and then the injector region. Okay, now the goal is to we could actually come back and come back to this. Let's actually go ahead and complete the boundary condition. So now we have defined the regions. Even though it's not done, we can assign these boundaries into regions. So the head is in the cylinder region. Liner belongs to the cylinder region. So I'm double clicking on this to get to this menu. Piston belongs to the cylinder region. Intake port belongs to the intake region. Exhaust port, the boundary, belongs to the exhaust region. Now EV top, exhaust valve top, it's the stem of the valve, that's actually in the exhaust region. The angle part is also in the exhaust region. The bottom is open to the cylinder. So we are going to put it in the cylinder region. This is actually discussed in IC engine lecture slides too. Intake valve top is in the intake region. Intake valve angle is in the intake region. The bottom is actually in the cylinder region. The inlet boundary is actually in the intake region. Outlet boundary is in the exhaust region. Hydrogen inlet boundary is actually in the injector region. Piston skirt is part of the cylinder region. Injector sac is part of the injector region. And so let me double check on that. In my data sheet, what I have, that's good. So no, I actually have to put this into the cylinder region right here. Tumble fixture is definitely in the intake region. Injector valve is actually in the injector region, and then the spark plug is definitely in the cylinder region. Now if I hit validate, you can see I'm done with the boundary menu. I'm not done with the regions menu because even though I have declared these 4 different regions, I haven't like given any conditions. So these are the initial conditions. So how do we define these initial conditions? So remember the start time of our simulation, it's the intake valve opening. So when you specify these conditions, you need to think about the start time because it's the initial condition. So the cylinder, what are the conditions in the cylinder at IVO? At IVO, the intake valve has not opened, so it's mainly the exhaust products that's in there, and the temperature is also quite high because the intake gas has not come in yet. So I would use 1039. Again, these values come from your engine testing. So if you have access to either GT power or actual measurement data, you can go to that particular crank angle and look at what this value should be. You can change these values if you want, or like you can actually use the default values. Now the products of combustion should be specified here in cylinder. So products of combustion is nitrogen, oxygen, and just water. So let's include those. So the water is 0.12761, oxygen 113357, nitrogen is 0.759002. It should all add up to 0. If not, you can actually hit normalize and it will add up to 1. Now, there are no passives defined. So my cylinder region definition, the initial condition definition is done. Go to intake, look at what the initial conditions are. It's 309. I can use it like from boundary as well if you want to, but I'll just 319, and the pressure I can use 1229. Now this pressure can come if you have a profile. You can look up what that value is, the crank angle is, and look at what that pressure should be. These typically come from a pressure transducer data from your engine testing. Here it's just going to be air because it's an inflow of air. And exhaust, again, it's going to be from your exhaust products. Now this is at high temperature, so it's at 800. The temperature, the temperature is after the exhaust stroke, right? So this is low now, 275.1 from my data sheet. This is combustion product, so water and oxygen and nitrogen. So give the numbers here, 1, 2, 7, 6, 1, oxygen. So these values are typically same as what you have given in the for cylinder because it's all exhaust gas, 0.759002. Okay. And then the last region to set up is the injector region, and this is going to be just hydrogen. Let's give 309.15. Again, these values that I put in here, you need to, like in your own engine, you need to look at what the engine data and include those. It's just going to be hydrogen and 1. And now the initial conditions are done. Now, one thing we need to define here is events because we have multiple regions. So you apply, done, you go to events. Now, events in events, we tell CONVERGE how to connect these different regions and how to disconnect these different regions. Again, if you're not familiar with this concept, I invite you to look at our Introduction to CONVERGE and the IC Engine lecture slides. This is very well explained there. I am going to have several events here. So there are going to be 4 cyclic events. So and cyclic events. I'm going to activate this, and then I'm going to add one event for actually one event is for events by region between cylinder and my intake port. Now the event is going to be a valve type event, and it automatically knows because there's only one valve lift profile between the intake region and cylinder, it goes and figures that out. The other one is for again cylinder region and exhaust region, and again this is going to be a valve event. Now for injector, if you want to open it and close it, which you should, it's again going to be between the cylinder region and the injector region, but now because there is no valve, it's going to be an open event. I want to open this at -137. That means the injector region and the cylinder region are going to get connected at -137, and it's going to close at -103.5. Again, these numbers should come from your engine test data. This is going to be a close event. And that's about the event. So now if you go back here, let's actually verify this. So at the start time of this thing, we wanted to start at -374. Now CONVERGE calculates what the IVO value is. So you can actually take 346 as your IVO, or like 346 minus 720 because this is period, and that's how you get there. Okay, so we have so far done boundary conditions, initial condition, events, and the next is going to be setting up your combustion model, source, and your turbulence model. Okay, so now let's actually set up combustion modeling, turbulence modeling, source for the spark. Now you can see CONVERGE, when we said this is an engine simulation, it didn't assume that we are going to do combustion, because you can do cold flow simulations. So we need to go to physical models and add combustion modeling, and if you want to do emissions modeling, you can add that too. And you want source and sink modeling for our spark plug. You hit apply, hit done. Now let's actually move on to combustion modeling. So we are going to set up detailed chemistry. Since we are going to run multiple cycles, I want this to be cyclic. It is 720 cyclic. It's a 4-stroke engine. Now you can specify the values here. That means if you specify a start time here and end time here, this is going to be for all regions. On the contrary, you can specify region based value. So you can see as soon as I specified that, it actually deselected all of this. And now you have to go to this menu right here and add a region. I only want to activate combustion in cylinder region. It saves some time. If you don't do that, doesn't mean you're going to have combustion in the intake port. But what CONVERGE is going to do is it's only going to check for combustion in the cylinder region cells. So less cells to loop through. It's going to be periodic. My start time is going to be at -30. Now this corresponds to your spark timing, right? and then I want to have combustion on all the way till EVO. So I give my EVO timing as 130. So that's done. I want the combustion cutoff temperature to be 600. This is, if the cell temperature is lower than 600, it will not go into the combustion solver. I want the minimum HC ratio to be 1E minus 10. And then move on to models. So it's going to be Sage detailed chemistry. CONVERGE can do liquids combustion and solid combustion as well. We are not going to talk about that. We are going to use adaptive zoning for this. Again, if you don't know about these models, I invite you to go through our lecture slides. Two binning dimensions are good: temperature and equivalence ratio, and this setup looks good. Sage parameters. It's a smaller mechanism, so I'm going to use a dense solver. All of this looks good. So now let's go ahead and check in the case setup. What is the problem? Oh, I haven't specified a field. So go here and I click on and say hydrogen is my field. That's great. Now under emissions modeling, if you want to turn on NOx, you can turn on the thermal NOx model. This is a passive based model. You don't need chemistry to be in your mechanism. You can see here in a detailed chemistry mechanism, you don't have NOx chemistry. But if you have your NOx chemistry, you will automatically get NO and NO2. But this is a passive NOx model that you can turn on. Turbulence modeling, we are going to do RNG K epsilon. So I would recommend you click on this button, set recommended model values, and then we are done. Then we move on to source and sink model. Now let's actually go ahead and look at our spark plug right here. So I am going to remove the head boundary and the liner boundary. So we zoom in close. And we are going to specify an energy source right about here. So go into case setup, source sink modeling. Again, I would ask you to review our lecture slides on engine source modeling. I want to have two sources, one for the breakup and one for the glow and arc phase. It is going to be an energy source. Limit temperature is 50,000. The value I want to the amount of energy is like 20 millijoules for this first one, and then the shape of this is not going to be a box, it's going to be a sphere. And from here you should do some measurements and figure out what the center of that source is. I know from setting up this case, it's at 4, 1. I'm looking at my data sheet right now. But if you don't, you can simply go to CONVERGE and measure that. 3 zeros, 6 1 0 6 9 5, and the Z is 0.00173196, and I hit validate and show the source. You can see it's okay, let's see the source radius. I need to give it as 005. Yeah, so this one looks like it's slightly outside. You can do a better measurement here and get it as well, but you get the idea, right? So CONVERGE gives the depiction of this source as well, where it's situated, so you can go and correct it. Motion of the source, it's going to be a stationary source, and source 2, or the source 3 in this case, the second source here, it's going to be at the same location, but at a different timing. So let's go to general. So sorry, I didn't actually do the temporal setup first. Let's go ahead and do the temporal setup here. So I want this source to start at -25. Where do I get that? From my spark timing. And then this source will go only for half a crank angle degree because the discharge phase is pretty small. And it is a cyclic because I want it to work for 2 cycles, and the cyclic period is 720. Source time multiplier 1 is good enough. Source 2, again, it's going to be starting at -25, but because this is actually the glow and arc phase, I want it to go for 10 degrees. So let me go back to my data sheet and verify that. 720, validate that. Here I want again 20 millijoules. So that means during half 20 minus 24.5 to -15, it'll be like 20 millijoules, but from -25 to -24.5, this will double up and give you 40 millijoules for that breakup phase. Again, the shape, it's going to be the same location, a sphere at 0.0419461, and here it's 3 zeros, 61, 0695, and 2 zeros, 173, 196. Again, where these coordinates come from? Your spark plug location. Okay, the sphere radius should be 0.5 millimeters. How do you decide that? What's the condition? So I actually, okay, so that's where, okay, let me copy that and sorry, let me do a Control C, and I go here and I actually, that, now I can correct it. So you can see here, so let me actually hide everything and then bring in only the spark plug so you can clearly see it is. There we go, right in there, that spark gap. Okay, I go to case setup, it's all done. Now the next step is to look at grid control. Let's look at like grid controls. Now for grid controls, Converge automatically only gives you base grid size, but for this case I want like 2 additional strategies. I click on grid controls, I want adaptive mesh refinement, and I want fixed embedding. Click on that. Now the base grid size for this case, according to my data sheet, it's 4 millimeters. I can take that. And then let's move on to adaptive mesh refinement. I want different strategies, several different strategies. For my first strategy, I want the cylinder region. I click on this. Now for the cylinder region, because there's combustion going on and there's flow going on, I want based on velocity, and I want AMR based on temperature. If I go on to velocity, I want a grid scale of 4. That means 4 millimeters divided by 2 to the power of 4 gives you quarter millimeter cells. Subgrid criterion for velocity 2.5. Let's actually, for velocity, let's use 3, level 3. So that means half a millimeter cells. Subgrid criterion is 1 meter per second. Now I want this permanently because there's always going to be flow, right? And this would actually help having a good turbulence field. For temperature, on the other hand, I want level 4 because we know hydrogen flame thickness is small. So I want 1 level finer, so quarter millimeter cells. Subgrid criteria can be 2.5 Kelvin. And this doesn't have to be permanent because there's not going to be combustion permanently at all times in the cylinder. It's going to be cyclic. Let's actually use a cyclic. And I want this timing to start when combustion starts. Remember, combustion start time in the combustion solver is -30, but the source start time is -25. So in the actual case, when you run the case, combustion will not start until -25. Why I give -30 is I want to be ready. The combustion solver needs to be ready. AMR should be ready when the spark starts. I want this to end at EVO. The cylinder cycle period is 720. Why EVO? Because there can be like small amount of combustion reactions going on, but majority of your combustion should be done like within 50 degrees after TDC or so. Okay, so now I think we are good for cylinder region strategy. I want another strategy for my intake region. So intake region, there's not going to be combustion, so it's just going to be velocity, and half a millimeter cells should be plenty. Again, this is going to be permanent because there's always going to be flow in there. Now, one thing to include here is the maximum number of cells. Again, we talk about these strategies, how you set this up in our lecture slides. So I want you to look at those lecture slides too. You can decide how many cells, maximum kind of cells your simulation would have. For this one, let's include 1,000,000 cells. Doesn't mean it'll get to million, but what it says is if you hit 1,000,000 cells, CONVERGE will keep running, but AMR will stop adding more cells into the domain. So that should be good. AMR strategy should be good. Now for fixed embedding, I want several strategies to refine certain areas of interest. Now the first one is your piston skirt. So if you want to resolve the flow in the crevice region, piston crevice region, I would use a boundary embedding. The boundary is the piston skirt, and it's going to be a permanent embedding because there's always going to be flow touching that, and a half a millimeter cell, so a level of 3, 4 divided by 8 to the power of 3. One layer is good enough. And I want my second embedding to be at the, again a boundary embedding, but at the EV angle. When the valve is closed, I don't want a lot of cell pairing to happen. I know my minimum lift is 0.2 millimeters. I want this to be permanent at level 3. So there won't be cell pairs happening at the valve angle. If you do it for the EV exhaust valve, I want to do the same for the intake valve angle as well. Again, permanent, level 3. And then for the tumble fixture, I want another embedding. Again, this is how you want to do embedding, which boundaries, and how many levels comes from experience and knowing your geometry and knowing some kind of information of the flow. So you don't have to do this for all the simulations that you do, but essentially knowing your simulation, your geometry, the flow helps you figure out what kind of strategies you want. So I decided 1 millimeter cells around the tumble fixture is good enough. Because you don't want to go overboard with this, have level of 5, 6 cells. It's good, CONVERGE will run, but it will run pretty slow because you are going to have a massive amount of cells. My next embedding is going to be a region embedding, and that's for the injector region, and it's going to again be a permanent and the region is the injector region. I want 0.5 millimeter cells in that region. And I'm looking at my data sheet, and I want a cylinder embedding, a shape embedding, level of 3. This is to, so there's 2 sets of like embedding. So this one is actually for the cylinder, the entire cylinder level 2, that's 1 millimeter. And then let me give these values, and I'll show you some of these things after I finish setup. And the radius I want, so this is to encompass the entire liner. You can see from the background, it actually encompasses the entire this. Okay, so, and now I want to add another cylinder to, this is actually interesting. I'm going to deselect this so you can see clearly. This is for the exit of the injector. Let me remove the head region, head boundary and the liner. So when hydrogen gets injected over here, we want a finer mesh. So because it can be like sonic or supersonic, and that's what we are going to do. Like we are going to have a finer mesh embedding over here, and we can do a cylinder embedding. And we don't want it like at all times, because hydrogen injection doesn't happen at all times. So we could do cyclic and save some cells when we don't want it. But I want it to be at least 0.5 millimeter. I want to start it at negative 137.5. If you remember, I start injecting my hydrogen negative 170. So I start this embedding a little earlier than that, so I get a like good turbulence field in there, velocity field, and I end it after the hydrogen injection is done. Now, the center, you need to like measure certain dimensions here, and I have already done that, and that comes out to be 0.30732,702, and this is 0.3058615, and the z coordinate is 0.0113778. And then the other end of the cylinder is at 0.3 zeros, actually 2 zeros, 692,77226, 0.30586 and 15. The z coordinate is 0.2049499898. And then I'm going to give this as a conical shape, so I'm going to change the radii of the cylinders. And you can see on screen how I got that. So you can achieve a conical shape looking embedding like this. So and then the next one is for the energy source. So we need a mesh around the energy source so that we have good combustion, the ignition and the initial flame kernel growth is well captured. And that I want it to be spherical, and it could be cyclic. Now this is going to be fine resolution. This is scale of 6 means like down to 62.5 microns. But I can start this just before the spark starts, and I can end this just after the spark ends. And your coordinates are going to be the coordinates of the your source. Actually, since I have actually done that already, let me go and copy this vector and then bring back and paste that vector right there. So the radius of this smaller embedding, which is at high resolution, is going to be 3 zeros and a 5, so that's 0.5 millimeters. And then the other one in the same location, I want to add in the same location another sphere, again cyclic level 5. In this case, that's down to 1/8 of a millimeter, starting at -30, -5, same vector, but the radius is 1 millimeter. So that's all the embedding strategies. So we gave few embedding strategies to resolve the flow around the valves when the flow comes, the hydrogen injection comes in, all throughout the cylinder, around the tumble fixture, and of course when combustion starts around the spark plug. And then we wanted some AMR strategies to talk about, to resolve the temperature field and the velocity field as well. And the next, so now majority of the case setup is done. Now you just have to think about post-processing. And let's quickly actually go into post-processing. And you could actually do temperature, velocity. You have a whole suite of like things that you can add. In the combustion, we can look at like react ratio and the equivalence ratio. If you want to look at Y plus, you can look at it. Under species, I'd like to look at certain species. For example, if you want to make a video to see how the combustion propagates, you can easily do that by adding hydrogen, oxidation, or like, you know, you can look at water because that's the product of combustion. And then you could actually go into these output files, so and select how often do you want to select your outputs. Do you want to select any species outputs? Do you want to select any interregions flow flag, interregions like flow output? That means from one region, when you move on to another region, this option says I'm going to save total mass flux, and that should be good enough for now. And let's move on to species output right here, and I'd like to do mole fraction, because then it's going to give me the total mass of each region. These are region specific, like total masses, region, total mass, the mass fraction, mole fraction, and their standard deviations. Now this is important to think about it, like the writing time intervals. You can specify a file if you want to. For example, let me show you this. This is for the 3D outputs that you look in TechPlot. You can go and say, okay, I want cyclic at -360. That's during bottom dead center. I don't want to, like, you know, select like a lot of, I don't want to, like, you know, save a lot of post files. So every 20 degrees is good enough. Then as you move to negative, like during compression, -140, let's choose save files every 5 degrees. And then as you come really close to let's say combustion time, that's like at -30, let's do every 1 degree. And then let's save at every 1 degree until, let's say, 50 degrees, and let's move back to 5 degrees, and then when you hit like EVO, let's move back to 20 degrees, because after that like you're simply purging out, and then because this is cyclic 720, you need to add this entry as well, and the cyclic period is actually 720, and you can give a name. Let me say twrite post, because these are post files, dot in, and I hit end. Now for text outputs, that is like your line plots, every 1/10 of a degree is good enough. Restart files, you can specify use a profile or like 10 degrees, that's fine. Now this is important. Sometimes like during injection it could actually take a lot of time. Let's say it takes to get to like 10 degrees, you need like, let's say, 2 hours during injection. This is an extreme example, but if something happens to your, let's say, cluster, the power went off, you don't want to like lose all of that like 2 hours worth of data. So what this comes and says, every hour, every 1 hour, dump a restart file. So that means you have decided either every 10 degrees or like 1 hour you dump a restart file, and you want to save only 3 latest restart files. So when you get to the 4th one, the first one will be deleted and you will maintain the latest 3 files. That's for output files, and then that's all. If you want, like, you could actually generate map files. Again, like mapping, restarting, these are all discussed in our lecture slides. I again invite you to look at those lecture slides, ask questions from support, and then look at some of these example cases that we have in Studio. So that actually concludes our case setup for the Sandia hydrogen engine direct injection case with detailed chemistry. Thank you.